Thank you. You didn't have to embarrass me. Good morning, everyone. Thank you for being here. Thank you for the organizers for the opportunity to talk about my work. So I'll be talking about uncertainty principles, specifically for these metaplectic time frequency representations. So I expect the first part of the title is clear, the second one, not so much. But we'll spend quite some time just defining these representations and understanding what they do and why we're interested in them, and then we'll look into the uncertainty principle. But before we do that, the usual speech before any talk. Everything I'm going to talk about is joint work with Karl-Heinz Gröchenig. Actually, I'm talking about the last 3 papers that we wrote together. So the first one is now almost a year old and was recently accepted. We're quite happy about that. The second one, we uploaded it on archive about a month ago. And the third one, the baby, is just a few days old, but I'm quite happy that we finished and I can talk about it today. Also, I would like to remind you, I'm not the only one talking about uncertainty principles today, so please stay. All the talks after mine will talk about different aspects of uncertainty principles, so I think you will find that quite interesting as well. The third point is to the quantum people. I'm sorry, the results are not really in the setting of quantum harmonic analysis, but rather everything is about functions, and it's an open question to all of you how you would do this in the quantum setting. It's not clear to me at all, so any of the steps could fail at some point. I'm not certain, maybe they do, maybe they don't. Maybe there are counterexamples to what I'm going to talk about. I would like to see any progress in this area. Okay, the fourth point, I think it's rather obvious. I'm giving a Blackboard talk because I really like those and I rarely get the chance to do that. That also means that if you have a question, you really need to ask it right then and there when it's on the Blackboard, because we can't go back to slide 5 in the end. Yeah, so if the object of your interest is on the Blackboard, speak now or forever hold your peace. Okay. Okay, that's the preliminary part. Let's do math. So the notation is as it was throughout in the other talks. Capital T is a time shift, capital M is a frequency shift. Together, they are time frequency shifts. Personally, I prefer the symmetric ones simply because I handle computations with them a little bit better. But that's my personal choice, so most things will work out with the others as well. And the SDFT, so just a little note, because not everyone did it like me. So my Fourier transform is unitary, so I have 2 pi i's everywhere. Yeah, good, you're happy with that, I'm glad. Well, what are these metaplectic time frequency representations? They're supposed to serve as a generalization of the short-term Fourier transform. So that is also something that we've seen throughout the week. It is an integral representation that's mixing somehow a function f and a function g with a partial Fourier transform. Yeah? So how do we generalize that? We generalize it through metaplectic operators. And what are those? Well, if you start working with this time frequency shifts, like it or not, in the first few computations, this matrix will pop up. Yeah, there's a minus over there. So it's the standard skew-symmetric form, or if you will, the standard symplectic matrix, and it clearly induces a non-degenerate bilinear form. Yeah? And the first algebra question, or linear algebra question that pops up is when is this bilinear form preserved? They define group, it turns out it's a matrix group. Lie group theory comes and says, oh, it's actually a lovely group. It's a Lie group. It's an extremely well-studied group. It's the 3rd classical Lie group. So in case you have any algebraic question, people probably already answered that, which is great for us. Why do we personally care about this group? Well, as you've probably heard several times and you're well aware, these time frequency shifts are a projective representation of R2D. And you can lift it to an actual representation if you move over to the Heisenberg group. And then the order here is long, I just noticed, I'm sorry. So I'm not sure why people had the idea to rescale, but someone asked what happens if you rescale a time frequency shift. Yeah, you rescale it with a matrix. Do you still have a representation? And that's not clear anymore because we're not in the Beurling setting, right? If you go over to the Heisenberg group, things are not as clear. And it turns out if you want to still have a representation, what you really need to do is you have to take a symplectic matrix. You have to preserve this form. That's just an algebraic consequence of the way the time and frequency shifts commute with each other. And it turns out that not only do you get a representation in that case, but additionally that representation has to be unitarily equivalent to the one that you began with, so the non-scaled one. Unitarily equivalent means a lot of things, but for us explicitly means that there is an operator which intertwines the two representations. So this is this A hat. For each symplectic matrix, there is an operator that does this intertwining, and it's a unitary operator. We call this the metaplectic operator of A. Now, one thing which is sort of obvious, I can rescale the operator, right? So if I multiply with a constant, you end up with a new, technically new operator, but effectively it's not like you gain any new information if you just rescale the operator. It's the same one up to a constant. And it turns out these operators are unique up to this multiplication, which is very much a point of discussion within NUHAG, right? As those here have already heard. So this constant here, as Maurice likes to say, is very important. And Charlie will say, well, does it? Do you gain that much new information from it? For the purpose of today's talk, no, you don't. So why am I talking about the fact that this is a Lie group? It's a Lie group which tells you there's a certain structure behind it, right? So you will have some sort of natural homomorphisms that you want to preserve. And there's a relation to some operators, and operators naturally build groups with the composition. You want to somehow control the group structure. You want to preserve it, because if you preserve it, you can use everything else you know from other areas of mathematics to apply here. Ideally, you have a group homomorphism. So what does that mean? It means that if I decompose the matrix into tiny, or not tiny, but elementary matrices, I should also, on the operator side, decompose the operator. Well, it turns out you can't quite do that, but you can almost do it. So this is the very important, and this is the key in the entire talk. If I have a product of two symplectic matrices, the corresponding metaplectic operator is a composition of the metaplectic operators of the two separate matrices up to a constant. Yeah, there's this constant. And the constant is of modulus 1, which shouldn't be too surprising. And in general, if you're working with these metaplectic operators, yes, the constant is important, and it's unavoidable if you want to have a group homomorphism. But today, it doesn't actually matter. Okay? Well, doesn't that mean, I think you have to rescale everything, don't you? Right. I mean, you rescale, you add sort of this Planck constant with all that, right? Oh, sorry. Okay. Thank you. I mean, it's the point that you have a representation. So the existence comes from representation theory. So representation isn't way too tied to rescalings. Okay, so why am I saying that this is a very important relation? It's important because in general, people tend, if they haven't worked with metaplectic operators, they tend to be mildly afraid of them. The point is they can look very weird and very ugly and very nasty. That's true. There's some which are just not hand manageable. But the point of this relation is to say, just like in linear algebra, if you have a problem with a huge matrix which looks complicated, if you do, for example, the singular value decomposition, maybe you'll probably read a lot of properties already from the decomposition. And that's sort of the idea here as well. Yes, maybe on the whole, it's something complicated, but if you manage to bring it down to a product or composition into simple ones, you'll probably understand it from the products a bit better. And of course, you can iterate this. So that is what we're going to do. We'll keep decomposing the operator until we reach something which we understand very well. Which ones are the ones that we understand well? They're the simple ones. So a simple matrix, so the lower block diagonal matrices, the symplectic lower block diagonal matrices that you find are precisely these shearing matrices. And the corresponding operator is very simple. It's a multiplication with a complex Gaussian. So this type of operator was studied, and I think everyone can sort of manage it, right? It's just a multiplication. It's very easily invertible, which is probably also obvious just from the formula, yes? Yeah? Yes. I'm not. Yes, so that's something that's a bit more lengthy, and if it's okay, I would put it under the rug and leave it for the discussion. Sorry. I think it will take up just a lot of time. So we are working, okay, here's the thing. We're working with a very specific choice. I'm going to choose the operators. I don't have to choose this one. So Maurice likes to put a different constant here. He likes to put an I to some power. I'm trying to tell you that for what I'm doing today, it doesn't matter because it's of modulus 1, and we're doing uncertainty principles. So the first thing you do with an uncertainty principle is put absolute values everywhere, and you will not see these constants. That's why I'm getting rid of them from the start. Anyway, as I said, we want to see what are the simple metaplectic operators, because that's our goal, to get down to a decomposition in terms of them. Okay, so the first one, I hope you agree, it's simple. The second one, even more. If you want block diagonal symplectic matrices, they have to be of the format an invertible matrix in the upper block, and below it's the inverse of the transpose. So that's what minus t means. And I denote them with d of L because they correspond to dilation operators. So it's just a rescaling, it's a change of coordinates, it's a very simple thing. At some point somewhere things have to be complicated, and the complication comes from this one. So the standard matrix will go to the standard operator. Its metaplectic operator is the Fourier transform. Okay? And this is the one which makes things complicated. Now, what do these operators have to do with the representation? Well, let's have a look at the STFT. The STFT is very commonly immediately written as a scalar product, so it will inherit a lot of nice properties from that. Someone will immediately say, oh, it comes from a representation, so it inherits properties from representation. The point of view here, or the way we reach the representation, is a bit different. So I think all of you will recognize, yes, this is a product of functions, but you can also see it as a rank 1 operator, or it's a tensor. So it's a tensor F tensor G bar. G bar because it's sesquilinear. And we're evaluating at the points t and t minus x. So I can see this as a function, not in d variables, but I'm jumping to 2D. But the point is, this here is a change of variables. A change of variables is a dilation. So instead of writing t and t minus x, I can very easily replace that if I choose the correct change of coordinates with some dilation. And I think many, or at least several people already mentioned it, and then you take a partial Fourier transform. Because the coordinates now are not just t, but x and t, we're only taking a Fourier transform with respect to the second part, to x. And the point is, I mean, I think people denote it often with F2. Well, F2 is also a metaplectic operator. If this is metaplectic and this is metaplectic, so is the composition. So I'm trying to say this is some A hat for a properly chosen A acting on F tensor G bar. And you see, this is how you get the generalization. People thought, well, I don't really have to dilate with this specific L, which belongs to the STFT. I can dilate with another one. And people have studied that before. And at some point, people thought, well, why are we really picking this specific metaplectic operator? I mean, you can pick any. The formula is valid, right? So I can write it down. And this is how we get to the first definition. So there are various names. If you ask engineers, it's something to do with linear canonical transforms. People that prefer the Wigner transform, they say it's a generalization of the Wigner distribution. I work mostly with the STFT, so for me it's a representation, but it's all the same thing. So the A Wigner representation, or distribution as it was first called, is simply A hat acting on F tensor G bar. And hereby, A belongs to 4D times 4D matrices, because we doubled the coordinates, so we have to also double the matrix. And F and G are initially in L2, but it's not too difficult to see that these metaplectic operators act invariantly on the Schwarz space, so you can also define them as functions from Schwarz to Schwarz, and that means that you can also extend them by duality on the dual space. Okay, now what's the point? Okay, a bit story time. As I said, it's not like I'm the first one that noticed this. Yeah, people saw it, work with it. And if I'm not mistaken, the first time this appears in this form, so a systematic covering of all metaplectic or Wigner, A Wigner representations, is due to Cordero and Rodino in a paper which was published in 2022, I think. So the paper is titled, begins with, correct me if I'm wrong, but I hope it's correct. It's Wigner Analysis of Operators Part 1. So if you were here for the talk on Tuesday, it was Part 3 already. So they wrote a series of operators. It turns out, I mean, they had a problem, and the problem had something to do with the wavefront. If you don't know what it is, it's a problem. They were interested in it, were solving problems related to it. And it turns out that this was rather helpful as a tool. And then the natural question is, of course, well, it behaved in that paper for that purpose well as an STFT. Does it behave in other type of issues as the STFT? So do you get modulation spaces? Do you get frames? What happens? How does it behave in pseudo-differential calculus? So they wrote a series of papers, picked up people along the way to write with them. And I'm sure they have a better reference list than me about it. So Charlie and I were only interested in the uncertainty principles. So the STFT comes with its own set of uncertainty principles. We ask, well, do these generalized versions do? When we talk about generalizations, most of the time, the generalization of an object, of an operator of class, typically carries over the properties that we want. This is not the case here. Yeah? So really, that's the point. It's not that we don't expect them to carry over. It's not a problem of carrying things over. It's more of a question of which ones do it. It's a problem of classification, at least for me. Why? Because we know examples where things are amazing for time frequency analysis. But you should always keep in mind you have a group structure behind it, which means that the most trivial operator of them all is also here. The identity operator is also on a metaplectic when it matches the identity matrix. So I think you can all imagine you will not get any meaningful time frequency analysis, at the very least no frequency, if you map the elementary tensor to itself. You've done nothing. Yeah, so you need to factor out all those trivialities. Another trivial ones are unfortunately the easy ones. So if I have an elementary tensor and I do a change of coordinates, you learn nothing about the frequency, right? You just change the coordinates, but the frequency is still not here. And the same with this multiplication. What do you learn if you just multiply your vector with a function which has no zeros? Nothing. So what I'm going to talk about today really is how to determine, how to classify the good versus the bad symplectic matrices or metaplectic operators. Specifically, I'll focus on uncertainty principles. So the ones, it does not mean that if it's good for one thing, it's good for everything else. That's also a bit of thing here. Anyway, as I said, they wrote a series of papers. They proved to be useful as long as you don't choose the ridiculous, trivial versions. They proved to be useful in various settings. Charlie and I, or not Charlie and I, Charlie asked me at some point, is this really everything? So yes, they are provably, clearly, this is a sufficient condition. So this equation is a sufficient condition to have a nice representation. But what is necessary to have a nice representation? And I come to the second part now. This is the content of the third paper, and my favorite part, I think. Why? So this is part 2. Why A. Wigner? What makes a representation good for time frequency analysis? Yeah, that's the question that we're trying to answer. So we want to do analysis, so some minimal form of continuity is necessary. Yeah. For reasons, I'm not sure why, but we decided to do sesquilinear. It felt also like a very small requirement from a representation. And the third, and the thing which really relates to time frequency analysis, is to have a covariance property. So something which we probably just take for granted all the time with the STFT or the Wigner transform, if I move my function around in phase space, or if I move it in time and frequency, the end result of the STFT is just a moved STFT in phase space. And that's what we want also. That's what we expect, and we think it's a minimal requirement for a representation to be suitable for time frequency analysis. And interestingly enough, it turned out that if you want compatibility with time frequency analysis, you have to work with these. And I found it really nice and rather surprising. And I'll comment what's the surprising part. So that was theorem 2. From a few days ago. What are we asking for? Can you see the blackboard? Is it okay? Okay. So, maybe I should go in the other. Let R be a mapping from the Schwartz space. So we're taking pairs of Schwartz functions and we're mapping them to tempered distributions. And we're assuming that it's, as I said, sesquilinear. In the paper, we'll write bilinear, but it doesn't really matter. It's very easy to jump from a bilinear to the corresponding sesquilinear form, right? As I said, we want a little bit of continuity. And because we have pairs, we're only asking for separate continuity, separately, and only weak star, because that was the weakest continuity that we could ask for. Continuous map. So not zero, otherwise things are trivial. Such that the following holds. There exists a measurable function, phi. It goes from R2D times R2D into R4D, such that, as I said, we want a covariance property. And what is a covariance property? If I shift both f and g, of course, you don't have to shift both. You can set 0 in other coordinates. But if they shift them around, I should end up, and we allow for a multiple if you wish, but it turns out the multiple is 1, so it doesn't matter. We want to end up with a multiple of the original. So it's rho of some phi, which depends both on lambda and mu, but not on the functions of R of f and g. Okay. Note, phi is not linear. Okay, that was very, if it's linear, it's essentially trivial, the whole thing. Then there exists a constant A and a matrix in SP 4D, such that this representation is necessarily an A Wigner representation, distribution. Okay. I'm not going to talk too much about the proof because I'm worried I'll run out of time, but I would like to highlight the surprising things. So thank you for pointing out that we're working initially on L2. This is the first thing which is a bit surprising here. We had something which was on L2 going to L2. We made the domain way smaller, so we reduced the conditions there. And we made the range larger, so we weakened the conditions. And yet we still go back to the metaplectic ones. Yeah, that cannot be avoided. The second part, initially this is separately weak star continuous. It turns out it's strongly continuous. That's not very surprising because with the Schwarz space, you should immediately think we apply Schwarz kernel theorem, so you get continuity there. So the powerful thing is this covariance property. Yeah, this phi function can be, you maybe cannot see. So phi can be initially measurable, yeah, it can be completely wild. Just because this is continuous and the time frequency shifts are continuous, that does not mean at all that phi is continuous. Yeah, there is no analysis type of approach to prove this. You really, I mean, the way we proved it is we use Lie group theory to argue the whole thing. But without it, it really gets weird. But what's really the key point? This covariance property implies something very interesting. So here phi can be wild. But these time frequency shifts come with a certain additivity. And the additivity on this side and the relation will imply a version of additivity on phi. The problem is that we have these tempered distributions here. So just a comment, remark 3. If I start with this representation, acting on any f and g, and I shift with lambda and shift back, it turns out if I iterate this, you apply it several times, you apply what you know about the interactions between time frequency shifts, you end up with some constant, you end up with a phase factor, we don't really care too much about that, and you end up with the following shift. We have phi of let's say lambda mu, sorry, no, not lambda mu, but lambda plus nu and mu plus eta. So if you try to push the additivity, minus phi of lambda mu minus phi of nu eta, and then what we begin with. What are you supposed to see here? It's telling you that the range of this representation, of this mapping, unless this is trivial. So if this is 0, then everything satisfies such a relation, right? The shift by 0 is no shift at all. But what if this thing is not linear? What if phi were not linear? Then maybe this expression here is not 0, which would imply this relation holds for all f and g. So the range of this representation would necessarily be very weird in the sense that it would have to be a space which is a subset of eigendistributions of time frequency shifts, which immediately excludes functions, right? If your function is in LP for p less than infinity, it cannot be an eigenfunction of time frequency shifts. So it would have to be, in a way, a very thin set. And that's just a very weird situation to be in. And it turns out it just cannot work out. Yeah? But you really need measurability. So once you drop the measurability, we're not quite sure what happens. And we suspect that there might be some very weird, very pathological example that goes into a subspace of eigenfunctions. And yes, there are, of course, we're mapping to the space of tempered distributions. Hans will immediately say the Dirac-Com is a potential troublemaker. So the question is how to avoid those. The measurability can fix that issue. The condition of measurability can be replaced by uniqueness, but we do not know how to do it, or if it works with neither measurability or uniqueness. Yes? Yeah. Yes. Yeah. Yes, but this phi, that's the problem. I don't know enough to apply Stone von Neumann. I do not know enough about phi a priori. That was.
Phi is not quite a priori.
No, that's the point. So when I say representation, I mean it in the analysis version, and then we show that it's actually in the representation theory. Yes, thank you. That's really the punchline, I suppose. Okay. Other questions about this? Okay. So this is our argument. Yes? Yes? Yes. This one? Yes, I'm starting with the pair. Here? Yeah. My apologies, sorry. Yes. Okay, thank you. Okay, thank you. Okay, now I don't have a lot of time, so I'd like to talk about uncertainty principles a little bit. So what is an uncertainty principle? It should be something familiar. We're asking about restrictions, about concentration on phase space. Yeah? So classically it begins with a pair Fourier function and its Fourier transform. So you have sort of time in one axis and frequency in another. If you put them together, you can read it as a phase space condition. And there are several types of uncertainty principles. So this is already part 3, I suppose. So specifically, I'll focus on phase space. And those that have been in the area probably know already the STFT satisfies essentially, not necessarily all, but it certainly satisfies the primary uncertainty principles which are known for a Fourier pair. Yeah, something like Benedict's, Hardy, Beurling, Gelfand-Shilov, all those things are satisfied in the appropriate language for the STFT and equivalently for the Wigner distribution. And our question was, can we replace these metaplectic ones there? Of course, they are the trivial ones that I told you are not allowed. The question is, which ones give you an uncertainty principle? And as I said, there are several types of uncertainty principles. So the simplest classification would be qualitative versus quantitative. Qualitative typically says something like, if the function is too concentrated in whichever way, then the function is actually zero. Qualitative usually has something of the type, if it decays so quickly, or if it's concentrated this well, then it is a Gaussian, or if you relax a little bit, it's a Hermite function or something like that. So those are the typical statements and the ones that I know. Or there is some constant and it's something to do with optimal constant and so on. So that's the quantitative part of it. I'll only talk about the qualitative because it's a bit easier to show, to demonstrate a qualitative one. But the proofs that I'm going to show you for the qualitative ones actually work in a quantitative version. It's just a bit more work to write out. So when I think of uncertainty principles, the first one is Benedict's because it's somehow the easiest one. Just like the Fourier pair, an STFT cannot be supported on a set of finite measure. And all these uncertainty principles are modulo the trivial version where something is zero, right? Because in that case, the STFT is simply zero. Unless you're in that regime, the STFT cannot be supported on a set of finite measure. The second point is something like Hardy. So an STFT cannot decay better than the STFT of a Gaussian. It has to be zero if it decays quicker, but others will talk about Hardy, so I'll let that be. And the one that I'll talk about is Beurling, because people say that Beurling is the nicest one, strongest one, whichever way you want to phrase it, because it implies a lot of other classical ones. So what is Beurling? In the classical, ultra-classical version, it says that f of t, or f of x, I suppose, f hat of omega times this exponential or weight if this integral is finite, R2d, then this already implies f is zero. Okay? The STFT version of this says the following. If I replace the Fourier pair with an STFT, so I'm writing here, I hope is it readable? No? Yes. Ah, yes, okay. Just, yeah. I'm replacing the Fourier pair with the STFT again at x omegas. A little technicality, the 2 has to disappear over here. But that's an STFT issue and not an issue of the uncertainty principle. If you replace it, then you end up with f tensor g has to be 0. So usually it's phrased like f is 0 or g is 0. Because we work with elementary tensors, we'll stick with that notation. Yeah? And what we want to do today here is replace this thing. The one thing which bothers me a little bit about, this is, first of all, the generalization. So the original is due to Beurling. If I'm not mistaken, Hermander provided a proof, and then others provided further ones, correct? Charlie? Yes, Charlie's nodding. Good. And this generalization with the STFT is due to Demonge. from 2005. I believe it was in the Journal of the London Mathematical Society. So how do we really place it? The thing that bothers me a little bit is that the STFT is a function on phase space. So you shouldn't be separating time and frequency. I know it's sometimes easier for the notation, but really, I want you to see this STFT not in terms of x and omega, but jointly in terms of lambda. Okay, so I'm going to write it out one more time so that it's clear. This is theorem 4. Zero 5. Let f g be in L2 if, so I'm stating a simplified version, they prove a quantitative one. It's just that for illustration purposes, let's do this. If the integral of VGF at lambda, again exponential. So what is this thing? It is a quadratic form in lambda. It is x times omega, which means that there is a matrix so that I can write it as pi of absolute value lambda times, I'm going to call it j tilde times lambda. It's not the j from above. It's really a different matrix. If this integral is finite, then f is 0 or g is 0, or equivalently f tensor g bar is 0. And if you think a little bit about the matrix j tilde is 1/2 of 0, identity, identity 0. So almost the standard skew-symmetric one, but it's symmetric instead of skew-symmetric. And it's just that it is. It's a matrix which describes this condition. Now, how do we replace it here? So this one is from the second paper. This one is 25. Let Fg be in L2. And we have a symplectic matrix. What is the condition on the matrix to get an uncertainty principle? If A is of the following format. There's a shearing matrix. There's a dilation matrix. I don't think they're really called dilation matrices. It just reminds me of the dilation operator. That's why I refer to them as such. Okay, we know that these sort of do trivial things. What is the complicated thing? It is a matrix A, B minus BA. So note the standard skew-symmetric form is of this format, where this is 0 and this is the identity. Such that U transpose U is not block diagonal. Then there exists a matrix. I'm going to call it omega, which will depend on the initial matrix A, such that a Beurling-type uncertainty holds. Yes. I'll specify it in a second. Sorry. Beurling-type UP holds. Hereby, U is a unitary matrix which is written as A plus IB. And this is a whole thing. It turns out that these are precisely the orthogonal symplectic matrices, so we're going down to the maximal compact subgroup of the symplectic group, and it turns out the group is isomorphic to the unitary group, but then you need to sort of go down in dimension. So this is 4D times 4D, this is 2D times 2D. Yeah? Yeah. So what I'm telling you is the key to an uncertainty principle goes down only to this matrix. You see there is no condition in terms of these, and it should be clear why. When it comes to uncertainty principles, this thing is absolutely harmless. It does nothing. It will disappear in the absolute value. This one will just change your integral, but the Lebesgue measure is invariant under dilation, so it's not a problem. And what does the uncertainty principle look like? I'll continue down here. If the following integral, so Wigner transform, a Wigner transform of f and g at lambda e to the pi, and now you shouldn't be too shocked, lambda times omega, this J tilde matrix, this is transposed omega lambda. If this is finite, then the elementary tensor is 0. Okay? That's the statement. So why is the key in this unitary matrix? First of all, if the unitary matrix were, if this product that I'm interested in were block diagonal, then things get ultra simple. Yeah? So remark, if U transpose U is block diagonal, then I can write this Wigner A transform as follows. There's a chirp. That's how engineers usually refer to this multiplication operator. The chirp is harmless. There's a dilation. The dilation is also harmless. And then instead of F, I get some operator, let's say A1, lower dimensional, and A2 acting on G. This thing cannot give you an uncertainty principle, because whether I phrase the uncertainty principle for F or F tilde, it doesn't matter, because F and this F tilde are related by a unitary operator. So if one is 0, the other is 0. So it's not that only this is an implication, it's more of an if and only if relation. Why does it work for the non-diagonal case? I'm going to go over there. So, proof, sketch, or just an idea. The point is the following. If you start here, so this is already, as I said, we'll want to start doing decompositions. Once you start decomposing this, and you know that there's a relation to the unitary group, so you do a decomposition there, you jump back, you do a decomposition which is easier to compute than on the symplectic side. And if you keep jumping back and forth, in the end you'll end up with the following expression. This A Wigner transform of f and g is some chirp, not necessarily the one that we began with. You also collect something from here, but it doesn't matter because it will disappear in the absolute value. You also have some sort of change of coordinates. This is where omega pops up. And then you have almost an STFT. You don't have the original functions. But whether I phrase an uncertainty principle for f or the unitary image of f, it doesn't matter. Really, the key point is that you go back down to an STFT. Not quite. It's a partial STFT. So what is the definition of a partial STFT? It's precisely what you might think. I'm only taking time frequency shifts in the first k coordinates. So we're integrating only with respect to the first k, f of t, and we're fixing in the rest, gt minus x1 minus omega 2. Minus omega 2 is just a technical thing, doesn't matter. And then again, omega 1 is used for the frequency shift. What does this thing look like? The prototype, this is F here. If G and F were tensors in the correct dimensions, a partial SDFT looks like the SDFT of F1 with respect to G1 times just F2 tensor G2. So what do we do to prove the statement that we want? We put this whole formula in the integral. This one immediately disappears. You do a change of coordinates with omega. This is where the omega pops up. Sorry, I hit it. I'm sorry. This is where that omega pops up, just a change of coordinates, relatively harmless thing. And then you need to prove essentially, so what we want to do is that the partial SDFT satisfies. Okay? That's the game. And it turns out it's pretty easy. So what happens, it's a bit easier to argue with Benedict's, but the proof, the moral of the story is the same. So if you assume that this entire partial SDFT is supported on a set of finite measure, let's say maybe even compact for my picture, I'm going to draw here R2 of D minus K. So this is for the variables that I fix, and this is for the variables where something interesting is happening. Yeah, this is the x1 and omega 1. So this is for x1 and omega 1. Well, it turns out up to a set of measure 0, whenever I restrict on any cross section over here, the transform looks like a true SDFT. And it's pretty trivial if you look at the elementary tensor. And what you do is you argue that in each cross section you disappear. Well, if you disappear on cross sections almost everywhere, you disappear almost everywhere. Yeah, and that what I'm trying to say is this proof technique had nothing to do with Beurling. It had nothing to do with Benedict's. It was just decomposing to something you know, and then just considering cross sections. So what we really did in the second paper was write down an algorithm how to move from an uncertainty principle, which is well known for the SDFT, to an uncertainty principle for this metaplectic time frequency representations. And then you can, of course, do quantitative versions of it, because you can also discuss things quantitatively. You have to be careful a little bit, because then the constants will depend on each cross section. But other than that, you will also end up with new uncertainty principles. So I'm almost out of time, so it's time for me to thank you for your attention, and I hope there will be some questions.